Good morning, Year 10. Welcome to this week's electricity lessons. And could you please now pause the video and complete the low stakes quiz in your notes? Okay, welcome back, Year 10. Make sure you've got a green pen in your hand and let's go through your answers to those. So, what happens when resistors are added to a series circuit? And the answer is the resistance increases. The battery is having to push the charges through more resistors. The equation that links potential difference, resistance, and current is V equals IR. These components are a light bulb, an ammeter, a fuse, and a voltmeter. Potential difference is the work done between 2 points in the circuit measured in volts with a voltmeter. What is the effect of light intensity on a light-dependent resistor? As the light intensity decreases, the LDR's resistance increases and the current flowing through it increases. These are questions that you should be starting to find comfortable. Some of them are more wordy than others, but in general, across the board, you should be starting to know what this language means. It is different, I don't doubt that. Okay, so today we are going to investigate the characteristics of various different components within a circuit. Some key words that we're going to be using down here, none of these should be new to you this lesson. Okay, so this is in a yellow box, that means that you need to write it down. So, ohmic and non-ohmic resistors. An ohmic resistor is one that will always follow Ohm's law. And what we mean by that is that we would always expect when we plot a graph of voltage against current, so we're going to put voltage on here, not quite right here, we would expect to see a graph going through the origin. The origin being, there we go, the origin being this part in the centre, so I would expect to see it being a straight line graph. Now, its gradient could potentially be different. Oh, didn't mean to do that. I wanted a different colour. It could go through the origin like so. That would still be an ohmic resistor, so that there is constantly a linear straight line graph between the current and the potential difference. A non-ohmic resistor will be different in terms of the fact that it might well have a curved line such as this. So the purple is a non-ohmic. Okay, that's the basis behind today's lesson. What we're going to go on now is go and look at, well, what is it? Which components is it that produce these different shape graphs and why? So the three that we're going to be testing today is a resistor, a filament light bulb, so not a LED style light bulb, but one where the filament, a thin piece of wire, is causing so much resistance that it gets really hot and glows. And that's what a light bulb used to be. We now use an awful lot of LED ones, particularly in school. All the lights in school are now LEDs, and they do behave slightly differently. And lastly, we're going to look at LEDs, and all the three of these produce different shape graphs. And by the end of this lesson, I need you to be confident in telling me which component will produce which shape graph and being able to identify that. Okay, so we move on initially to testing a resistor, and I'm going to show you the circuit here, and then we'll look at the shape of the graph. So in our circuit, we have got cells which are making up a battery. We've then got a variable resistor, and the reason we've got this variable resistor is so we can vary the resistance, so we can vary the voltage that is going through our resistor. We're then measuring the potential difference over the top of our resistor, and in series we have an ammeter. So the voltmeter is being connected in parallel with the resistor, and the ammeter is connected in series. Now, I'm just going to take you off and show you a website that is going to help with us explaining this. So this is where those diagrams have come from, and very, very similarly. So what I can do here is, you can see I can vary the voltage that is going through. Unfortunately, I'm still on LED and I want to be on resistor. There we go. So I can now vary the voltage that is flowing through my resistor. And as you can see, as I vary the voltage, the current is also varying. Now we're going to start and we're going to plot some points. So up here we've got, we're going to start with the cells the right way around. Okay, so we've got a high voltage, and that is plotting us a point up here on our graph. As we lower the resistance, if I come down to here, I have got a lower voltage. Sorry, if I increase the resistance, and another point, decrease the voltage some more, and you can see I'm getting a dead straight graph there. And if I go right down to the bottom here, I should be able to get one bang in the center. So that shows me that I've got a straight line graph. Now, what I can do to see if this continues into this quadrant, and this is important and you'll see why when we get to the LED one, is that I can reverse the cells. I can plot the point again, and now I'll increase the voltage that is being applied across the resistor. And you see again, my graph is a straight line graph. What that means is that this resistor is an ohmic resistor. It obeys Ohm's law at all measures of voltage. And that is because it is not necessarily getting particularly hot. Temperature is not having an impact here. Okay, what do you need to draw for this slide? So you need to draw this circuit, and you need to make it obvious that the voltmeter is in parallel to the resistor that we're measuring, and that the ammeter is in series. You then need to sketch the graph. You don't need to accurately plot it. I need to see a graph where you've got current on the x-axis, voltage on the y-axis, and we've got this straight line relationship. So that would be a graph that you would draw a line of best fit with a ruler. Okay, pause the video there while you do that, and then carry on. Okay, the next one that we're going to look at is we're going to look at the light bulb. Here we've got exactly the same circuit drawn, but this time we've now replaced the light bulb with, so we've replaced the resistor with the light bulb. We've still got the ability to vary the resistance around the circuit, and therefore to change the potential difference being applied across that light. And we've got the ability to reverse our cells. So with a relatively high potential difference on our light bulb, we'll plot our point now, and going to come down gradually, and we can see as we plot these points, this time the line is starting to look a little bit different, and it looks more different as we get closer to the origin. And you can see here that we have a curve. Very low voltages, it does start to look like a straight line. If I go back up here a little bit and put some points in here, there we go. but very quickly this line curves. And if I reverse the cells, we'll be able to see that this process happens very similarly in the opposite direction. And what we end up with is a graph that looks a bit like an S. It is symmetrical, it is exactly the same. It doesn't matter which way the current is flowing around the circuit. We get this S shape where it's almost straight between -1 and 0 between -1 volt and 1 volt, but then we've got this quite definite curve. And so what this tells us is that a filament lamp is a non-ohmic conductor. It does not always obey Ohm's law. And the reason it does not always obey Ohm's law is because the temperature has a significant effect on the resistance of the wire. And the hotter it gets, the less resistant it is. Okay, pause the video. You don't need to draw the circuit again because actually the circuit is the same, you've just changed the component, but I do need you to sketch the graph. So again, y-axis of voltage, x-axis of current, and let's have a sketch of this S, making sure it goes through 0, 0 on the origin and then back out the other side. Okay, pause the video while you do that and then come back and we'll carry on. Okay, so now we're going to look at an LED. And what we've got here, and this time actually I'm going to start with my potential difference very low, which is a little different from previous ones. So at 0, we've got no current flowing around the circuit at all. Now we increase it a little bit, but I've gone the wrong way. Excuse me, let's go the correct way. Right, so we can see there, it doesn't matter that I've increased the voltage, we still don't have any current in the circuit. And I can go up, and I'm going up until I now change the current. So looking at the amp meter, and I've got to get to about 1.3 volts. So at 1.26, it is still completely flat. Now, once it does start to go up, you'll notice it goes up rather quickly. Ooh. Now, if I take the potential difference up any further, current has exceeded the LED and has burnt out. So what you notice here is we've got a very rapid ascent from 0 to a very high current in terms of milliamps. Now we are now recording in milliamps because a LED is so much more sensitive. And as I'm coming down, I'm just putting more dots on my graph, and you can see that even changing the potential difference by 0.01 of a volt has quite a significant difference. And that comes down gradually until we get back down to 1.3, and at 1.3 it goes back down to 0. So what we've got there is we've got a very different looking shape graph. Oh, what about 1? That's going to fill the gap in. Now, so flat, 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 and then it goes very sharply up. And the most voltage that that LED can handle is less than 1.5. So as soon as I went over, and actually as soon as I went on to 1.49, it blew the LED and I couldn't get any more. So we've got a very, very rapid increase in current being able to flow through. So basically what that tells us is that an LED has got to have a very controlled potential difference flowing through it, otherwise we're going to have some issues with that. Now, if I reverse the cells, and this is interesting on this one because actually, if you notice, my point, it doesn't matter flowing through the other way, there is no current, and that is because current can only flow one way through an LED. And that's shown by that graph. So what I need you to do again, don't worry about drawing the circuit, although it might be worth noting that this time we are talking about milliamps, not amps. And then I want you to sketch this graph. And the key factors here that we need to pay attention to is it doesn't start increasing straight away, but once it does, it increases exponentially fast until you get to the point where the LED would be burnt out because too much current would have been applied. Okay, pause the video and draw that for me. Okay, so here in the PowerPoint again, if you've missed anything, you'll have a chance to pause and just have a look back. So we've got our straight line graph for a resistor. We've got our S-shaped graph for a filament light bulb. And we've got our very flat until we get to 1.3 and then exponentially quickly increasing graph for our LED. And there is nothing happening when you reverse the circuit because an LED will only allow current to pass through one way. The other way, the resistance is so high that current cannot pass through. So we've got those three shapes of graph. I want you now to think which graph is which component. You need to know this. This is actually an exam question. So just pause and make sure you're aware of this and comfortable with it. Okay, so a resistor at a constant temperature is a straight line graph. A filament light bulb is the S-shaped graph. And the diode is this graph that is flat and then very quickly, exponentially increases. Okay, I'd like you to pause the video and work your way through and use the keywords at the top and where you've got a choice of two words, select which one goes before you go on to the next slide where it will give you the answers. But I would really like you to have a go at this prior to moving on. Pause the video and then come back to go through the answers. So, when the voltage was increased across the resistor, the current increased. Okay, I'm going to need to add in some across the resistor. Yep, so it tells us that we're talking about the resistor. So this is the graph where we've got this straight line. It does go through the origin. The voltage was increased across the bulb. The current increased, and so what happened there was we were having this S shape. And that was due to the bulb getting hot. That gives the circuit more electrical resistance. And then lastly, the LED, which is quite a different graph. When the voltage increased across the diode, the current increased after 1.3 volts. The graph shows that it was proportional, but it was only proportional once we got here. In fact, no, I'm going to change that. I'm going to say that that is curved. No, we'll leave that because it is proportional after a certain point. And that is the diode only allows flow to charge in one direction. Okay, moving on then. I'm now going to ask you to pause the video and attempt this exam question. It's attached to the lesson as well, so it's not just on the screen. I appreciate it is very small as it is on the screen at the moment, so have a go at that exam question and then come back and I'll go through the answers. So pause the video for me now. And we will go through the answers to this. What's going on with my mouse? Okay, so the first question says, describe how the student could set up a circuit to find the resistance of a lamp. You should include a circuit diagram in your answer. So what you need to be drawing here is the circuit diagram for where we were investigating the lamp. So we need a battery. We need an ammeter in parallel. We want a variable resistor, and then we want our lamp. We must make sure that all of these are connected, and we want our voltmeter in parallel across our lamp. Then we want to be writing, and I want to find a different colour pen. Then we want to be talking about the fact that we will measure the potential difference across the lamp. And then that we will calculate the resistance using V equals IR. And although I've drawn the variable resistor here, this is the bit that you don't actually have to have. You can put it there because it's there in the experiment that we've just done. But if you haven't included that, but you've got the ammeter in series and the voltmeter in parallel, you would still get both marks for that. You then need to get a mark for drawing the circuit. You've got to talk about the fact you're going to measure the potential difference across the lamp. And you've got to talk about the fact that you're using V equals IR to calculate the resistance. Student is given an electrical component in a sealed box. She has to find out what the electrical component is by experiment. The student records the current and potential difference for the component, and her results are shown below. Explain how... Oh, you can't see. It zoomed in, actually. That's better. Explain how the student could know that the electrical component in the sealed box is not an ohmic conductor. And the reason behind that is that the current is not directly proportional to the voltage. And it would be in an ohmic conductor. So we know that because we know that if this graph had been a straight line, that would show us an ohmic conductor. We know enough about ohmic conductors to know that if we've got a curved line on a potential difference versus current graph, that it's not an ohmic conductor. What is the electrical component in the sealed box? So we've got to look at this graph and we've got to remember, well, which of the three components that we tested in today's lesson gives us that shaped graph? And you should be able to come back and go LED. D. And your explanation behind that, oops, sorry, I'm scrolling on the wrong screen, is that it is an LED or a diode. You would get a mark for LED. And that is because it has a high resistance negative potential difference. So that is here, this is showing high resistance. And then the graph is curved, and then a low resistance for positive. And that tells us that current can only flow through it one way. Okay, and then the final question is asking us to use the graph to determine the resistance of the component at 2.3 volts. So you've got to look at the graph, and this is a little bit hard on screen, so I'll show you how you would do it on paper. Now, there are two possible ways that you could go about this. You could, first of all, you need to find 2.3 on the graph, and that's what the bit I say that's quite difficult. And then you would go up to, draw your line up to the graph. Now at this point you could either draw a tangent on your graph and work out the change in x over the change in y, or you can work out what I would equal. So from my graph I've got V equals 2.3 and I've got I equals 1.2. And then I can take my equation, V equals I R, and I want to work out what R is, so I'm going to divide both sides of my equation by I, so I end up with V divided by I equals R on its own. The I's would cancel out on this side, and so then I can put 2.3 divided by 1.2 into my calculator. And I come out with 1.96916. Which is interesting. It's not correct. It is absolutely what I'm coming back with. Okay, I'll look into that and come back to you. But that's certainly what I'm working it out from there. Okay, well done for that today, Year 10. So, the main thing that I want you to take away from today's lesson is knowing the shape of these graphs. You must know that a diode is going to go flat and then up sharply. You must know that a lamp graph will be curved, and you must know that a resistor at a constant temperature will be a straight line. Make sure you upload to me your notes, which include showing drawings of these graphs and the gap fill exercise, and also your attempts at the exam question. Now remember what I've said previously, make sure you are using the same numbering convention. So I'm expecting to see question 1, A, B, C, D. I'll look forward to seeing your work later on this evening. Thank you very much, Year 10. Have a lovely rest of your day.